Greetings and welcome to the Introduction to Astronomy. In this episode of Special Topics in Astronomy, we will talk about spectral lines and how astronomers use light to uncover the properties of objects throughout the universe. So let's get started. How can astronomers determine what a distant star is made of when they cannot travel there and collect a sample? At first, that seems like an impossible task, yet astronomers can identify the elements in stars, galaxies, and nebulae located trillions of kilometers away. The key is hidden within the light those objects produce. When light is spread into its component colors, it reveals patterns known as spectral lines. These patterns contain information about the atoms that produced or absorbed the light. And by learning how to interpret those patterns, astronomers can uncover remarkable details about the universe. Atoms are not continuous systems. The electrons can occupy only specific energy states. An electron cannot exist at just any energy. It can only occupy certain allowed states. When an electron moves between these states, it must either absorb or release a precise amount of energy. That energy appears as light of a specific wavelength. Because every element has its own arrangement of electrons, every element produces a unique set of wavelengths. The result is a distinctive pattern of bright or dark lines within a spectrum. These are spectral lines. In many ways, they function like fingerprints. Just as fingerprints can identify a person, spectral lines can identify an element. When astronomers collect light from a star, they pass it through an instrument called a spectrograph. The spectrograph separates the light into its individual wavelengths, producing a spectrum. Within that spectrum, astronomers look for characteristic patterns of spectral lines. For example, hydrogen produces one set of lines, while helium, sodium, and calcium produce others. If those patterns appear in the spectrum, astronomers know those elements are present. This technique allows scientists to determine the chemical composition of objects that are far beyond the reach of spacecraft. But composition is only part of the story. The same spectral lines that reveal composition can also shift, broaden, or change in intensity, providing clues about the physical conditions of the objects producing the light. A single beam of light can contain an extraordinary amount of information. Spectral lines are used throughout modern astronomy. Astronomers use them to study stars and determine the elements present in their atmospheres. They use spectral lines to examine glowing nebulae and learn about the gas between the stars. They analyze the spectra of distant galaxies to understand how those galaxies evolve. And they even use spectral lines to study the atmospheres of planets orbiting other stars. In each case, the underlying idea is the same. Scientists collect light, identify spectral lines, and interpret what those patterns reveal about the source. The methods changes very little. The objects being studied may be vastly different, but the physics remains the same. Spectral lines transformed astronomy from a science of observation into a science of physical understanding. Before spectroscopy, astronomers could measure positions and brightness. After spectroscopy, they could determine composition and physical conditions. This technique allows us to investigate places we may never visit directly. It turns light into a source of evidence, and it provides one of the most powerful tools available for understanding the universe. Every star, nebula, and galaxy sends light into space. To our eyes, that light may simply appear bright or colorful, but hidden within it are patterns created by atoms and molecules. Those patterns allow astronomers to uncover properties of objects across immense distances. By learning how to read spectral lines, we learn how to read the universe itself. So that concludes our discussion on spectral lines. We'll be back again next time for another episode of Special Topics in Astronomy. So until then, have a great day, everyone, and I will see you in class.